my great pleasure to welcome you all to today's colloquium. Yeah. Our speaker today is Professor Masashi Hazumi from KEK in Japan, and he's currently a visiting professor at NCU in Taiwan. Yeah. So as an experimental physicist, Hazumi-san explores particle physics and cosmology, probing the fundamental nature of the universe and space-time. So early in his career, so he played a leading role in the Bell experiment at KEK's B factory, so where the development, where he developed the silicon vertex detector, and as leader of the analysis group, so he contributed to the discovery of the CP violation in beam meson decay. So this provided a critical test of the Kobayashi-Masashi theory, and later this is recognized by the 2008 Nobel Prize in Physics. Yeah. So after that, he jumped into the experimental cosmology, and so he did also became the funding leader, PI of the Lightbird satellite mission for CMB polarization. And he is also a key leader of this Simons Observatory for CMB experiment in Chile. Yeah. Okay. See, he also served as the founding director of the QUP at KEK. So that is aiming to advance novel measurement methods with the quantum sensors. Yeah. So for his contribution, so Hazumi-san received the SPHEREx in 2008. And in 2023, so he was appointed as a member of the Nicholas Copernicus Academy in Poland. So today he will talk about this, new opportunities in Taiwan with this Simons Observatories. Let's welcome the Hazumi-san.
Okay, thank you very much for the comprehensive introduction. I prepared my self-introduction, but probably I don't need to do that. Sorry, yeah. So let me just skip everything. But just a couple of things. After I turned to experimental cosmology, I've been chasing the CMB B mode to test cosmic inflation. I worked on Quiet, Polar Bear, Simons Array, and LIGO. And I'm a member of Simons Observatory, but since I've been really spending lots of time on Simons Array and LIGO, Simons Observatory, my hope is to launch a new group in Taiwan here, and so that I spend more time on Simons Observatory. And then last but not least, I'm always happy to work with theorists to propose some new measurement methods. So that's sort of myself, and then in short, I'm a particle physicist looking up the sky. So that's how I define myself, an experimental particle physicist. So then Professor Yuki Inoue at NCU invited me to work together on the study of gravitational wave landscape. I'm gonna tell you what that means in a minute. So I serve as a visiting professor from August for 3 years. Actually, I started some preparation visiting professor position already in April, but now it's renewed, and then from August for 3 years, plus alpha, hopefully, under the support of CHIP, which is a research center at NCU. So my task there is to launch a CMB team and join Simons Observatory. As I told you, I'm already a member of Simons Observatory at KEK. And so the landscape of gravitational wave, what I mean by that. So this is Yuki's slide, I just stole that. So he's been focusing on this LIGO, high frequency gravitational waves. And CMB B mode can address the primordial gravitational waves, and then in a completely different way, not really observing, this time dependence, the usual, the gravitational waves in the usual sense, but this CMB B mode is the most sensitive probe for the super low frequency. So, and then in between, in the future, you might expect to get some more information from other probes, such as 21 centimeters, hopefully. So it's a long-term vision that we should really focus, try to explore the landscape of gravitational waves to see what's going to happen. So that's the vision of Yuki. So then I'm helping him at NCU. So that's more or less introduction, but one remark. In October, Professor Akito Kusaka of University of Tokyo will visit the ASIAA and give a seminar on cosmic microwave background and Simons Observatory, in particular on small aperture telescope development and the V-mode search. So in order to avoid much redundancy, my talk today is designed to avoid such redundancy as much as possible. That's a remark. So having said that, here's outline of my talk. So after giving CMB projects overview, I'm gonna give an overview of Simons Observatory, and then jump to the science with the large aperture telescope of Simons Observatory, and then I'll touch on plans in Taiwan before summarizing my talk. Okay, so as you well know, the cosmic microwave background, the CMB, was discovered in 1965, 60 years ago. Pinjas and Wilson got the Nobel Prize, and the modern interpretation is once the universe was hot and dense, where electrons, protons were separate, but when the universe got cooled, the protons captured electrons and formed the hydrogens formed, and then that time, after that, photons traveled freely. So that's evidence of the direct evidence for hot Big Bang. And then in 1990s, this COBE satellite showed the proof of blackbody radiation of CMB, and they also discovered the CMB temperature and isotropy, which indicated cosmic inflation. And Mother and Smoot got the Nobel Prize in 2006. After that, two more satellites, WMAP and Planck, were launched and then improved this CMB temperature and isotropy measurements a lot. And then also ground-based big telescopes such as SPT and ACT also added this temperature and isotropy observations at high L. So now, thanks to that, now we come to precision cosmology. The model-wise, we call it lambda CDM. So then question is what's next? And obviously for CMB, the answer is polarization. So in May, we had this CMB at 60 conference in Torino. And then a lot of CMB scientists got together. I also was there as one of panelists. And then if you are interested in that, you can visit this webpage, and YouTube videos are also available. This is really a sort of a nice snapshot about the current CMB observations and future CMB endeavor. So, that's one information. But when you hear the CMB 60, that sounds a bit old. 60 is just one, great Chinese cycle of the years. But what I'm stressing here is that the first observation of CMB polarization was in 2002. So CMB polarization is still young. It's like 23 years old. And why people are excited about polarization? Well, because that allows us to test cosmic inflation and quantum gravity. So what's predicted is that when we had the inflation, primordial gravitational waves were generated. Then after that, when CMB was emitted, that primordial gravitational waves affected CMB polarization, so that if you look at the CMB polarization map, you should be able to find the CMB primordial B mode, the curve pattern, as a fingerprint of inflation. And this is by far the most sensitive probe of the primordial gravitational waves. So that's why people are excited about that. And then a little bit of my research history. This was like 11 years ago. And then when polar bear, which I was involved in, first touched on so-called this lensing B mode signal, not the primordial. That was the first sort of touching the lensing B mode in 2014 in March. And 2 weeks later, there was a famous bicep 2 claim. They claimed the discovery of the primordial gravitational waves. The signal looked like that, and then that was a sensation. And then in Japan, even the biggest newspaper, Yomiuri Shimbun, put this the headline, a really big announcement. And there are a bunch of papers trying to describe that. I remember even some of the papers sort of suggested giving up quantum theory, and then sort of all the excitement happened. Turns out that that was due to the dust emission. After the combined analysis with Planck and bicep KEK, that signal disappeared. And then now this is 2016, and then we improved measurement, and this is the current situation of the CMB spectra, temperature, and E mode and the B mode, and this is TE. So lensing B mode has been much better measured, whereas the primordial B mode is still not measured. There's the best limit coming from bicep 2, KEK, and Planck are this level, where R is tensor to scalar ratio, which is basically showing the intensity of this primordial B mode signal here. And then the limit is like 0.13. And we have good reason to pursue this down to eventually 0.001 or so. This order of magnitude. So that's what people are really chasing. So because of that, there are actually a bunch of projects ongoing. So I explained this polar bear, and that was upgraded to Simons array, and in Chile, Atacama, Chile, and then ACTPOL, and converted to advanced ACTPOL, and then also there's a class project, and ACTPOL polar bear was merged to Simons Observatory, which is the main topic today. And then if you look at the South Pole, SPD pole upgraded to SPD3G, bicep 2 KEK, and then together collectively you call it South Pole Observatory. And there are also other projects in Canary Islands, Spain, and Argentina, and Tibet. There's this early CPT in preparation. And there are some balloon-borne projects, Spider Flu, EBEX Flu, and LSPE and Piper in preparation, I think. And in space, Lightbird is proposed to JAXA, and JAXA selected Lightbird, and we are in the early phase of studies. So there are many projects like that chasing this B mode. Okay, so that's the current scene, and then let me look at the Simons Observatory. So Simons Observatory is one of such projects, but it has much broader scientific topics. So this is site view, and then we have, as I can show you in a minute, we have 3 small aperture telescopes, and the one, here, large aperture telescope, called SO nominal. In addition, we plan to add one more small aperture telescope from Japan, 2 more small aperture telescopes from UK. So together, this is going to be the Simons Observatory, and then it's supported by Simons Foundation and national and many other national institutions and funding agencies. And So we had a collaboration meeting in July in Manchester. Here's this group photo. We have, I think, right now total like 400-ish researchers on board. And then closer look at SO telescopes. I took some photos in December last year when I visited the site. There's 3 small aperture telescopes. One of the inside is looking like this. We got a first light in 2023 and started taking data in 2024. And then this large aperture telescope commissioning happened in 2025 this year, and we got first light in February. And we plan to have a wide survey. This is for small aperture survey. We plan to focus on the region with small foreground and cover like 10% of the sky. And then for those who are interested in some technical details, I put this information. We're gonna observe CMB with 6 frequencies with this beam size and noise level. And if you look at the large aperture telescope, it can even do the wider survey, which is gonna have quite a good overlap with other projects such as DESI, Rubin, Euclid, and DS. So that's search strategy, and it's gonna, in particular, this large aperture telescope, that is gonna give you a lot of science, and from cosmology and particle physics, and planetary science, galactic astronomy, time domain astrophysics, extragalactic astronomy. So in short, the catchphrase is that the Simons Observatory science ranges from the last scattering surface to our solar system. And another way to define SO, Simons Observatory, is it's like super ACT or super SPT. So all results from ACT basically will be superseded by this SO. So if you have ever read ACT papers, everything done by ACT will be superseded. And if everything works fine, you're gonna have this temperature anisotropy. This is E mode, and this is P mode, and you can really extend the error range up to like 5,000, and then you can have this very nice B mode. There's B mode, and search for primordial B mode down to this blue points are for SO, so down to like L of 30 or so. So just to as a recap, E mode is a divergent even parity mode, looking like this, and B mode is a current odd parity component looking like this. Now, just one page about the forecast on the tensor to scalar ratio measurements with SATs. SO nominal expects to obtain the error of 0.003 or so. So roughly speaking, we expect order of magnitude improvement from the current limit. And this is based on detailed studies of foreground removal. I'm not going to go into details, but then with that precision, you can really test some interesting models. And then, so you have a chance to have some big discovery. And actually, my main passion as a particle physicist is on this tensor to scalar measurement. But again, as I told you at the beginning, Akito is going to give you some more detail. He is also one of the experts of this small aperture telescope and the tensor to scalar ratio measurement, P-mode search. So instead of going into more details, just let me go to large aperture telescope science. Okay. So large aperture telescope science, if you are interested in more details, you can just take this QR code, and then this is for this archive preprint, which it's just recently accepted by JCAT. So if you have time, just you can take this QR code. By the way, when I served as a director of QUP, I met a guy at Toyota who really invented this QR code. It was a really big discovery, and I heard about the story of this invention. It's fun. Okay, the Large Aperture Telescope. This is a ground plan. We are here, we got the first light, and then we are at the same time proposing this advanced SO project to NSF. So we already have the pretty much filled optics tube, but we are even more ambitious to fill more. So if everything's fine, we're gonna really have this. We at least have this 3 to 4 year observations with the current configuration, and with upgrade, we hope to really continue our measurements for next 10 years or so to really get the unprecedented precision. Let me just give you some the latest, some sort of snapshots this year. So this is sort of a new project, like kind of a baby raising. So you should see lots of photos. Like when you raise your baby, you are proud to show lots of pictures to other people. So this is the first light in February. This is just a Mars, and then this is preliminary, of course. This some image of galactic center, and then this is an example of a single 20-minute galaxy observation with 4 bands, and then this is still very preliminary pointing correct. So preliminary meaning pointing correction is not fully implemented, but this is 144 hours of observations at 90 gigahertz. And this is a lab early map, compact sources found and fit and subtracted with a model of the beam. So we are really excited about the initial, this testing. This is still testing, not for statistical, measurements. Just a demonstration level. This is a lab lensing map from 144 hours of observations. With cosmic infrared background, meaning a cloud 545 gigahertz overlaid in red and blue. And then this also very preliminary lab lensing and CIB cross correlations. And then so far so good and very exciting. Of course, we are really working hard on all the nitty-gritty details of the systematics and then the analysis details. But here, I'm going to show 2 pages of tables showing the science goals from a SOLAT survey for primordial perturbations. One thing is this scalar tilt. We plan to reduce the error by factor 2, and then we expect to get much better optical depth measurement, and then non-Gaussianity improvement by factor 5. And then about the relativistic species, this number of effective, the light particles basically, but the error current is 0.2 or so, and it could be down to 0.045 or so. And as for neutrino masses, some of the neutrino masses, they also expect to get clear improvement. And then these with check marks assume to use other probes. So in that case, together with galaxy surveys, for instance, we can really get down to this level of uncertainty. Then that could be decisive to determine the nature of the neutrinos the hierarchy of neutrinos, for instance. And then as for the accelerated expansion, sigma 8, improvement factor 7 will be expected. And then continuing to the list for the galaxy evolution and reionization, plus the catalog. If you look at that, this order of magnitude or even more number of AGNs will be identified. And as for galactic science, you see also this lots of improvement like this. And the solar system science, also huge improvement. And also very interesting transient detection will be carried out. So lots of great sciences. Just several snapshots. The constraining the properties of primordial perturbations. Of course, people's main focus is on the tensor to scalar ratio, this vertical axis. Sorry, I forgot to put this R. But the horizontal axis, scalar tilt, is also very important. And then we expect to have the current error bar. So that's going to be very interesting. And as I told you already, non-Gaussianity improvement is also a very important, probably together with other probes, such as, although I'm not writing that, SPHEREx is going to improve that. And then also, we, together with the overlapping galaxy survey data, we plan to really improve this non-Gaussianity measurements. One more thing about the N sub S. This is a slide Andrew showed at the CMB at 60. What he pointed out was, if you look at the latest ACT result, which indicated some shift of the N sub S observations from the previous observations. So this ACT shift of N sub S, if this is correct, he argues that this could be highly significant because it disfavors inflationary models with an exponential approach to plateau with N sub S of around 0.956. So we should see. And then, of course, nice thing about this is that ISO is going to give us better precision measurements. So, but for many observations, now the name of the game is systematic uncertainty. So we should be extremely careful when you discuss such things. N sub S, when you talk about E mode, using E mode, and that has a large Deborah, and which helps to better determine N sub S. But then at some point of a large L that might suffer from some beam uncertainty, for instance. So all that sort of uncertainty should be taken care of very carefully. And refined image of earliest snapshot of the universe, we should be able to improve current limits on the number of relativistic species. And then that will give you maybe some hint of maybe some anomaly. For instance, you can rule out at 95% confidence level any light spin two-thirds particle that was in thermal equilibrium at any time back to reheating. So, well, this is exciting to particle physicists like me. Maybe not very exciting for astronomers, but this sort of science can be done. And then this can also be related to Hubble tension. So resolving Hubble tension with new particle physics models, that a lot of people are discussing that, and that can increase the Hubble constant, genetically, and that can imprint signatures in the CMB temperature and polarization, namely E mode, on small scales. So the full SO survey data will discriminate among such models. And as you know, the late universe observations and early universe observations, meaning from CMB, differ by like 5 sigma today. And again, the name of the game is systematic uncertainties. if you talk about possible like 10% difference, you really should be absolutely sure that your systematic uncertainties are under control at 1% level, which is a challenge. And then as for CMB, we believe that that's really clear. I mean, because CMB is in a linear regime. But truly nice thing is that SOE mode can add more measurements and then can improve this Hubble, early universe Hubble observations. Let me talk about another recent anomaly. So I saw a slide from Eiichiro Komatsu. So he's keen on this EB correlation observations, and that seemed to give tantalizing hints of the signal. Since E mode is even parity and the B mode is of parity, and we expect that naively in standard cosmology, the signal should be 0 if parity is conserved. And then, but there's no guarantee that parity is conserved if you start thinking about some new physics. So, so currently there is an observation by this WMAP Planck, and recent observation by ACT is like this. Together, this we see some 4.3 sigma significance. One thing I ignore here is all the detailed studies about foreground contaminations and possible systematics of the angle measurements calibration. Skipping that, I should say this is intriguing. And then, for instance, if this is due to dark energy, this measurement will rule out dark energy being a cosmological constant, stuff like that. So it's very intriguing. If established, that can be a discovery of the century. And so observations will give us a definitive answer. Now, coming to this cross-correlation, a new large-scale view of dark matter baryons and galaxy clusters, and a detailed analysis of the deflection of photons due to gravitational lensing from large-scale structures, and the scattering of photons from ionized gas in galaxies, groups, and clusters offer exquisite tests of structure formation models and allow constraints on the physical parameters governing those processes, particularly via cross-correlation measurements as enabled by the SO-LAT survey sky coverage. So this large sky coverage is exactly meant for this cross-correlation studies. And then here, this is about the new large-scale view of dark matter baryons and galaxy clusters, and then characterizing the energy efficiency of feedback in galaxies sourced by supernovae and active galactic nuclei. It is a major focus of galaxy evolution studies. And feedback is also the dominant physical uncertainty in optical gravitational lensing analysis that seek to constrain dark energy. Combined with measurements of large-scale structure from DESI, Rubin, Euclid, SO maps of integrated electron pressure in the momentum from the thermal and kinematic SZ effects will uniquely measure the baryon content in galaxies, groups, and clusters. So that's a quantity not measurable with optical telescopes, and will constrain the feedback efficiency to that few percent level. So here I show the stacked images of ionized gas density around galaxies measured via the KSZ effect. So this is measured ACT plus BOSS and the simulation for SO plus DESI, SO plus Rubin. So as I told you, SO is kind of a super ACT, so whatever ACT did can be done much better with SO. And then in particular, weak signals like KSZ, you might enter really the new phase. So that's really one of the exciting things that SO can offer. And one page about time domain. we are developing the time domain pipeline, and then we're gonna show the daily update, and then light curves of all sources will be shown and shared, and then we also plan to give transient alerts issued to the public within 30 hours of data collection. So, so this is really a millimeter wave unique opportunity, and then the goal daily sensitivity is shown like this. So this pipeline is in preparation, and hopefully will be instrumental, will be operational in a couple of years or 3 years. So that will also give us much more insight about this sort of transient phenomena. So now Taiwanese participation. So Yuki at NCU and I are making an effort to form a new CMB team at NCU. And the main project is the Simons Observatory. And Yuki participated in the SO collaboration meeting in July as an observer and got a lot of information. And we already shared a proposal from NCU gravitational wave group with the SO management. And the internal review of the proposal is in progress already. And then some researchers in Taiwan outside NCU are also interested in participating in SO. And these are the fantastic new opportunities for cosmology in Taiwan. Here are a couple of remarks. As I said, this review is in progress. I hope to deliver good news soon, but as of today, all the proposals shall obtain SO's collaboration approval, so please do not take them for granted. Thus, do not spread the wrong message that SO data already guaranteed to be accessible. Although I pretty much cautiously optimistic about that. So if you look at the NCU proposal, we are interested in cosmology, this correlation of COBB for primordial gravitational waves, and B times Z for cosmological parity violation, and E times Z for Hubble tension. And then the team is, so we have collaborators in Japan, in US, in UK, in Italy. So we're gonna have a tight collaboration. So members, including new postdocs and graduate students, can gain great international experiences out of this collaboration. So that's the current status. Then next very important step is to make it Taiwan-wide. And then in my view, SIAA is of course the center of the astronomy in Taiwan, and ASIAA's participation will be the key to the next step. In particular for leading astronomy, astrophysics, and cosmology with SO LAT data. And then for the sake of that, we're going to have an informal meeting next week during this cluster workshop on Thursday from 2 to 4 at SIAA room 1203. This is organized by Yuki, Ikwan, Teppei, Keiichi, and myself. The aim is to hear related science broadly and gauge interest in joining SO. And I invited Leo at CISA, who is working hard on galactic science using LAT at SO. So he'll give a short summary of SO LAT science remotely. So all people here are welcome to attend, and then even giving short presentations are really appreciated, encouraged on any topics connected to CMB data. CMB itself, or dusty galaxies, galaxy clusters, Milky Way, ISM, CIB, KC, polarization, etc., whatever you are interested in. I'm really happy to learn what peoples are working on, and then my purpose is to help Taiwanese science. So please come. Just feel free to come. Another is we plan to have mini workshop in November 6th and 7th at NCU as a kickoff of Taiwan SO activities and gravitational wave landscape studies. So we're going to have invited speakers from Simons Observatory. The confirmed speakers include Colin Hill from Columbia and Yuji Chinone from KEK. And we expect to have talks by the NCU gravitational wave group. And then talks by physicists and astronomers in Taiwan who are interested in SO are very welcome. We're going to soon send an announcement. And once again, every astronomer and physicist are welcome to join. So this is summary. The SO has begun observing the CMB sky with unprecedented precision and is expected to lead CMB observations in the next 10 years or so, starting to produce new results from the next year or two on many topics in cosmology and astrophysics. We have started the process for forming an SO group in Taiwan, and the first one from NCU is in progress. So the take-home message here is that SO will provide a new, hopefully new connection between astronomy and physics in Taiwan. And I hope that will be good for Taiwanese science. So we would welcome your participation and appreciate your support. Okay, that's all. Thank you very much.
Thank you, Hazumi-san. So, questions?
So you mentioned about the ineffective.
Uh-huh.
So on which scale do you put constraints? You mentioned reheating, right? The reheating is
After reheating, yeah.
like a MEV scale.
Sorry?
MEV scale is so you put constraints on the ineffective at MEV scale or other scales. I'm curious about the scale you put constraints.
Scale, you mean?
Energy scale.
Energy scale. Ineffective is basically very small mass, right? I mean, I'm not sure if I'm answering your question correctly, but it's useful to search for any light new particle. Yeah. Light is meaning really light, like below 1 electron volt.
May I ask a few more technical sort of observational questions? So you have multiple bands. Do you always observe all bands simultaneously? And you mentioned about the transient size. So how often do you go around the sky? What's the sky? Is that sky count?
For large aperture telescope, I showed you this one, and basically this can be covered. Well, this can be covered. Let's see. Well, this one obviously we can cover daily, and then this one it depends on the scan strategy. But what we do is typically this so-called constant elevation scan, and then this angle can be really large. So very roughly speaking, nearly this size. Almost every day, so that's rough answer. Yeah.
And that's always simultaneous for all bands.
Simultaneous for
all instruments.
For all instruments. Yes, basically that's true. Yes. Yes. Yes for large aperture telescope, we just have one big 6-meter dish. And we have 3 small aperture telescopes, which are independent, but basically we are doing the same, pointing the same.
So I'm curious about the difference between LAT and ACT. So they have the same mirror size, and so obviously has more frequency bands. So that will allow you to
Yes.
have a better
6 bands, yes.
foreground removal.
Uh-huh.
But I don't suppose you can get to smaller scale.
Smaller scale with
So
LAT. So here is the LAT beam size at FWHM.
yeah, I remember you have a power spectrum.
Yeah.
A slide with power spectrum.
Yeah.
That goes to very high L.
Yes, up to 5,000. Yeah.
So, to which L can ACT go to?
ACT is yeah. Actually, for some reason, this doesn't include ACT plot, but ACT can yes come up to 5,000. Yes.
And the reason you can improve upon all these other measurements is because it's more detectors.
More detectors, yes. It's really ridiculously gigantic. It's really impressive when you look at. Here's a person here, and then this is the receiver, cryostat. It's really impressive. Crazy big receiver, yes. So we have more detectors. That means each time we cover a larger area. So that's the reason. Yeah.
So
regarding the EV correlation,
Yeah.
You said something about measuring angle can cause this or something like that.
Oh yeah. If you miscalibrate your angle, you can create non-zero EV. Yeah.
So it can be because of that instead of parity violation.
Exactly. Right. So now you need to be careful.
So SO will be careful.
Yeah, so hopefully we'll be careful enough. And then how we do the calibration is really an interesting experimental business. And then we invented several things, including this drone calibration technique. And some people are even proposing to have a satellite just shooting the ground-based telescopes for the calibration purpose. But this drone and then some technique called a sparse wire grid calibration and then several other things. So we hope to get down to the precision level good enough to establish the signal. So that's one of the experimental challenge.
So how frequent do you need this beam calibration with external beam?
Not angle calibration.
Yeah, for angle, yeah.
Yeah. Oh, it's a good question actually. For instance, the wire grid is not in situ. You need to put that. So periodically, I don't know. We haven't decided, I guess, every season or stuff like that. And then for that, yeah, I mean drone, you can. I think for drone you can do that more frequently. But yeah.
I have another question.
Yeah.
Which is so light bird might be coming in 2032, right?
Yeah, a bit later probably, but yes.
So light bulb will be able to measure the low multipole region.
Yes.
So is ASO going to work with light bulb to
hopefully, yes.
Get a joint data set or something?
Yeah, hopefully, yes.
Okay. Is there any talks regarding that?
A good question. Actually, yeah, of course we know each other. And then we will probably have some MOU, hopefully, because we had MOU between Lightbird and CMBS4. We had a joint simulation study work, and was a nice work. And now CMBS4 is terminated, unfortunately. So it's a natural thing to think about this ISO Lightbird joint studies, probably. Of course, big difference is ISO already getting data, so it's a difference.
I was questioning once astronomers whether they're getting to know what the negative mass. Negative mass is the center for all the detection how they work on the detection of the negative mass. Does that mean whether there are experiments that's fine. That's negative graph, negative mass. Whether that's has to do with wasting a
So your question is about the neutrino mass?
No. You know, just we really have negative or negative mass. Whether that's going to be that really understood, and hope to figure out what is the most important subject.
So if someone can help,
Just it's not that it's you, but I think all the way to get whatever the improvement be.
improvement on
And the understanding of
sorry, I cannot answer. Probably we can discuss that offline. Okay.
Yeah.
Okay.
Okay. We try to address. Yeah. Other question? Okay. So as Hazumi-san mentioned, so next Thursday. So during this cluster workshops, there are going to be this informal discussion session for the Simons Observatory science. So please join this discussion. Okay, and thank you for coming. And let's thank again Hazumi-san for the nice, very nice talk. Thank you very much.